Hello everyone, good afternoon. Let me pull out my chat. I hope that you guys had a good weekend. Any questions before we start with the lecture today? By the way, I'm looking into your submissions for assignment 2. They're looking really, really good. I apologize because I couldn't finish grading them earlier, but I hope that for maybe later today, tomorrow, at most you guys will have the comments and the feedback posted in the assignment Dropbox. And of course, if you have any questions, feel free to reach out. Anyway, any questions about assignment 3? And I also apologize because I forgot that last Friday was a holiday, but we will have, as I mentioned in the email, we will have the office hours tomorrow at 1 p.m. in addition to the ones on Friday as well. You guys okay? No questions about the assignment? So I have a question about Sina. Can you post sample results of the function with updated data? Oh, sure. I can do that. Yes, that's right. Let me double check. But yeah, you're definitely, because the data is updated. Now, one thing that you may notice though, is I think the example is for the month of October. Let me double check. I'm trying to see this. Let me share the browser. So let me see. That's why I pick a particular month. So right. So this is for October from last year. So I can double check that. Actually, let me see if I have my we can do it live, but I think it shouldn't have changed. It's true that sometimes, because you know how is the data collection process, sometimes they update all records if they found mistakes in the data. So yeah, I see Minshin also mentioning that you got different results. Let me double check. Let's do this live. Let me just look at my solution. Assignment 3. So I'm going to, okay, let's do this. Let me check. So let me move. It's my, sorry, I lost my Zoom thing. Okay, stop share. And now let's share the desktop so we can run this together. Desktop 1. So I'm going to bring the results next to the thing. Oops, didn't work. Where are we going? Sorry about that. Okay, maybe a little bit small. Let me run also my script. So this is what I post in this in the assignment. So I'm going to source my process toward COVID, and I'm going to run my process store. Oops. I might have called it differently. Let me call it wrapper function. 2020 10. Yeah, so I call it differently from the name I gave in the assignment, but it's the same function. You can see it's obtaining the data now. I hope you guys can see. And I'm getting, okay, so look at that. So there are 4 different cases. So 9,047 cases from a total of something. The close contact didn't change, 565. Household contact 1272, 772. Okay, there's a change in the number of cases due to outbreaks and healthcare institutions. they updated apparently the cases with no information. Yeah, I can update these numbers. I'm surprised they didn't. They did change from October. That's why I picked a few months ago. But yeah, oh, look at that. They changed the pending. So as you can see, the backlog is not just from a few weeks ago, but is sometimes from months ago. I guess that's good somehow. But yeah, I will update. This matches more or less the numbers that you are seeing for the ones that you notice a difference in the results. Okay, that's good then. Thank you, Minshin. Okay, yeah, and certainly I will update the numbers. So if you notice discrepancies sometimes with the numbers, just let me know. We can double check all the time. But yeah, you can see that that's one of the tricky things with working with slide data. Even when it's data stamped from few months ago, you know, it can change. It's part of the things that happen with real world data, let's say. Okay. I definitely will update these numbers. All right. And as I say, if you guys notice any other discrepancies, just let me know. Any other questions? I think that you guys are doing very well, I can see. That's great. That's great. Okay. So if you guys don't have any questions, let's get started with the lecture. We are going to be talking about file input and output. And there is a good amount of material. I'm not sure we're going to cover it all, but we can see how far we can go. Just let me remind you, for those of you who join us later, that tomorrow we will have the office hours, and I apologize again for forgetting about the holiday on Friday. And of course, we will have also the office hours on this Friday as well. So for today, the idea is to talk a little bit about basic file input and output operations. That is usually known as I/O. A little bit about file system theory, because that's where we basically store our files. And then we're going to have a conversation about saving data in text format versus binary formats, and the different binary formats that are available in R. Okay. So that's what we planned for today. So, whoops, sorry about that. So let's talk a little bit first about basic file input and outputs in R. So the idea here is that, you know, independently of R or the programming language that you use, our data is stored in files. That is for preservation purposes, meaning that if you reboot your computer or you do something, the data will remain there, accessible. It can be read, it can be saved, it can be moved, right? And the way that we organize the data is, there are different names or conventions, but the way we usually organize is in a set of folders or directories. And within those folders or directories, we can have more folders or directories, and then we can have files. So for instance, I can have a folder 1, and then another folder hello, and then a file in that folder called word.txt, or within the hello subdirectory or subfolder have other files, and so on and so on. And the way to refer to this is, okay, if I want to give the location of this, I can say, okay, in folder 1 / there is the word.txt file, or in folder 2 there is the file not.txt, or in folder 1 and within the folder hello there are whatever other files it is. So another way to think about this is you have these folders, and within the folder is another box containing more files. That's another folder, or there is a file within that folder, and so on. So the funny thing is that, again, depending on the operating system, these folders and files are essentially the same thing for the operating system. They are considered files, sort of. The only difference is that there are different attributes or different features in what is a folder or a directory and a file per se. But, you know, formally speaking, or structurally speaking, for the operating system are kind of the same thing. The important thing to bear in mind, and this it has shown up in some of the assignments as well, is we need to be aware where we place those files and directories or folders, and depending how you do it is how you refer to the files or the folders, meaning the path that you give to find a particular file or folder. Now, we have seen some of these commands, at least in some lectures ago. This is how we do some sort of directory, and I'm using again as the same thing, directory or folder. So how we do some directory or folder management. So for creating a directory or a folder, we can do dir create, and then between quotation marks, the name of the directory we want to create. We can inquire if a given directory exists by doing dir.exist and then the name of that directory or folder. We can get the working directory, meaning in which particular directory or folder R is going to be looking for files that the path to this particular file is not specified. So for instance, if I do get working directory on my R terminal, it will say home sign and Marcelo. If I do it in the terminal where I was, let me show you that. If I do in the terminal where I was running the script, if I run get working directory here, then it will say a path that is quite long, because I usually organize my workflow or my folders so that I can easily find them. So it will say users Marcelo classes BCH2024, blah, 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 2021, this year, assignment, solutions, and then assignment 3, where I posted I store my solution for the assignment 3. And you can see the path is pretty lengthy, but that is how I organize. And if I do, for instance, the dir command, which is one of the ones I have in the list, it will show the files I have there. I have my main driver script in this case and my utility file. Let's go back. So that's what get working directory. In the same token, you can use set working directory to change the path. This one I have mentioned to some of you because you were using that in some of your submissions, to please do not use it, because for instance, if I want to run my script as I was running before, and I set the working directory to this very lengthy working directory that I have, and you try to run it in your own computer, it won't exist. It just won't exist. The user won't exist. Probably you will call your things differently. So that will make the script fail in your computer. So the set working directory is something that we usually don't have. We don't suggest or recommend to use it because it breaks the modularity, breaks the robustness of the scripts. So it's usually better to use just assume that you are in the directory where you can find the files that you need, and then work from there. The dir command I shall show you, it shows the list of files in the current directory, similarly to list files. Okay, so a few commands that are useful to manipulating and working with directories and files. Now, for files in particular, similarly to dir exist, we have file exist. And this one is very handy to check, for instance, if you are reading data for a particular file, or if you want to check that your source is going to work, and your utility files are there. You can do file exist. You can do also file path. You can do dir name to actually obtain the whole name of the path where the file is located. So a few commands that are quite useful sometimes to get a handle of, just to deal with the data file manipulation business. Okay. Any questions about this? All right. So I mentioned this because this is related to data manipulation and file manipulation, but let's see how we can write to a file. Okay, and there are a few different options to do that. First, we're going to see how to write to a text file, basically a file that you can open and it will have text, so it's readable by humans. So you can use the function file, and then you specify the name of the file, and in this case it's going to be called output.txt. And then the second argument to this function means that you want to write to that file. So actually what the file command does, it gives you a handle to a particular file. And so in this case, the file will look for a file name called output.txt. It will open it as for writing, so for saving information into the file, and we'll assign this into a variable f. So this is called the handler of the file. Now, how we put information inside the file? Well, we use the function write lines. And basically this function, as you can imagine, will write different lines of text inside the file. So write lines hello and the handler F. So you need to specify where you want to write this into the file F. You can have multiple files open, as you can see, and write lines word. It will put hello and word inside the file F. And then very importantly, we need to close this file. Otherwise the file won't be closed. It will remain open. So we need to close the file, okay? Alternatively, one can say write, the function write, specify the file name, file equal output.txt, and then what we want to write there, hello, okay? Now this will override the file if it exists. If you want to append, to keep adding stuff to this file, the syntax is pretty similar. It says write the name of the file, what you want to write, but then you need to specify append equal true. So you keep adding things and not overwriting the file. A third way to do this is to use the cat command that we have seen for writing to the screen. You can say cat hello to, for instance, the name of the file, and again, append equal true, so it doesn't overwrite the file. Overwrite means in this case, it basically eliminates whatever it was there before, because it recreates a new file and with the same name as the one that existed. So basically, the previous file is gone. Okay. There are other options, quite more involved or with more. I would say there are more functions with more options for saving data. In the same way that we have read CSV, we have write CSV for saving data frames, or write table is an equivalent as well. So if we need to save data frames, probably write CSV or write table are the ones we want to use instead of write lines or write text. Okay, but this is mostly for text files. Another option, this one is sometimes useful if you are, investigating something interactively in the terminal, is to use the sync command. The sync command is a funny one, because what basically sync does is all what you write in the terminal is dumped into a file. So for instance, I have an example here of an interactive section in R. So I'm writing 2 plus 5, the result is 7, and then I'm going to do sync and the name of a file. So for instance, sync output2.txt, and then I'm going to do print hello. Notice that now no output is coming to the terminal. I just say print hello, print do a bunch of stuff, 2 plus 5, and nothing of that, which should result in something coming back to the terminal, is displayed. This is because it's being synced, it's being redirected into this file output2.txt. For turning off this syncing behavior, you do sync and then you write capital letters null. That stops the syncing, and then you do 2 plus 5 and you again recover the result being printed to the screen. If you are using the terminal as I do, then you can look inside the file that was generated, or you can just double click on the file, and you will see that the previous commands, the result of the previous commands, were actually saved in this file. Okay, so this is more if you want to keep a log, a record of the commands, the output, the result of the commands that you issue in the R session. If you want to see both in the terminal and the file, you can invoke the sync command using split equal true, and then it will also save in the file, but also display in the terminal if you get like nervous because you're not seeing what is being printed by the commands. Okay. Unfortunately, as I said, it just saves the results of the commands, but not the commands per se. All right. Again, sometimes can be useful if you want to keep a record of the results of the commands that you issue. Now we have talked. Any questions so far? We have been talking about saving data as text. Let's see how we can read data from these files. So for reading, we saw read.csv for reading data from either the internet or files located in our computer. For reading text files, which are slightly different from the comma-separated values, the CSV files, we can use the read lines functions. As we have the write lines functions, we can use the read lines functions. And basically, by default, the read lines functions read all the content of a file. So for instance, again, if I specify the particular file, for instance, the one that we just generated with the sync command, and I put this in a variable f, which is the handler to the file. So file output 2.txt, and then I do read lines f. Now you can see that it's returning a sort of vector containing each of the lines that we wrote there. Okay. Alternatively, we can assign this to a variable and then look at the structure and see that actually this is a vector of strings, as I was telling you just a second ago. Again, whenever we read a file or write into a file, we need to remember to close the file. This is for the integrity of the file itself. If it remains open, it can be seen by the operating system as corrupted. So it's very important that either when we save data into a file or we read from a file, to close this file. Okay, there are other functions that you can use. As I say, read CSV can be used for reading data from comma-separated values, formatted files, read the link, read tables. Many of these can be tweaked a little bit with the arguments of the functions to read text file or read CSV file. So there is kind of a main function underneath all of these that allow you to actually acquire any kind of text type data, basically. Okay. All right, so this is a comment. I may skip this, but just as a comment, if you use a Linux type environment, and when I mean Linux type environment, it can be a Linux terminal or it can be a Mac OS. It may also work in Windows terminal, but if you need to, for instance, match all the files starting with a particular name. So for instance, I have here 3 different files: output.txt, output2.txt, output3.txt. This file has a pattern in their names. They all start with the word output, and they have the extension .txt. So one easy way to basically grab them all together or to look at them all together is to specify this pattern. So remember, the dir function listed the files in a particular directory or folder. And so I can say dir, and if I do parentheses, it will show all the files. But if I only want the files that has this particular pattern in the naming, so I can do pattern and then use this fancy function glob2rx. Don't worry about the name, means that it's using regular expressions. That's what the rx stands for. So global to regular expressions, that's what the name of the function means. Then I can do quotation marks and use the star, which means basically match anything. In this case, it will be match anything that ends in .txt. So this particular function will show all the files that ends with the extension .txt. I could just say quotation marks output star.txt, and it will only show the files that begins with output and ends in txt. Again, it's a handy trick to bear in mind when you are processing files with a particular pattern in their names. Okay. Any questions so far? I used to have this, well, not exactly this assignment, but a similar assignment to assignment 3, where I give you a list of files, which they are named in more or less in the same manner. Like in the case of the COVID data, it could be COVID or October, November, and so on. And then if I ask you to process all the years, you will use some techniques like this, right? Like COVID, Tor, and then star, and then 2020 or 2021, or depending on, you know, what you want to process. That's why it's sometimes useful to keep this kind of notation. Any questions so far? Okay, so let me show you an example of what is considered bad practice and good practice in terms of reading data or doing input-output operations. That's what IOPS stand for, input-output operations with files. It turns out that in any computational pipeline, in any program that we are running, writing and reading data from files is always the most expensive part. And this is because of the hardware. Computers are a combination of elements. They have a lot of circuits, which are really fast because they basically can process things at very fast speed. But when we need to save data, we are going down to mechanical components, basically spinning disk or even solid state devices. But even in those cases are still the most or the lowest part in the computational processing. So that's why minimizing the amount of input-output operations that we do can substantially have an impact in the performance of our computational pipeline as an overall thing. On top of that, if we do things, of course, we need to say data and read data. There's no question about that. That has to be done. Otherwise, we won't be able to say the results that we are acquiring or processing data. So there is no question about that. But there are different ways in which this can be done. And sometimes you find these kind of mistakes, not on purpose, of course, but just by not considering the overall design of the program. So sometimes it's important to bear these concepts in mind. Try to minimize IOPS, try to minimize the way in which we access for reading or writing data, because that is going to be very expensive for our program. So this is a very simple, naive example. You will basically see this right away. And we say, I will never do this because this is silly. And of course, the example is to just show you face-to-face with this reality. But sometimes, again, think about other cases, like the cases I have seen is on people processing DNA sequences or bases, and then it's not so obvious that you are doing this, but at the core you are doing this. So the idea here is to try to translate this into more generic scenarios to try to avoid that. So let's jump into the example. So on the left, I have something that again is going to feel artificial because of the example, but it's something that is done sometimes when processing data. And on the right, I have the good approach to do this. So in this case, I'm defining a string, hello world, and then I'm using the function string split of the string, and then quotation mark means by every single character in the string. So basically what the string split is going to return, it's going to return a list, and then the first element of the list, that's why there is the bracket 1, is each single character, a single letter in the hello world string, even the space, okay, separated with quotation marks. So then what we're going to do is we're going to loop over, you saw this in the assignment 2, in the third function, for I, my looping variable, in a string split, the same thing, basically loop over every single character. And this is where the actually bad thing happened. I'm assigning the handler of the file, hello world.txt, appending means add to that particular file, and then printing into the file, saving into the file each single character, closing the file, and doing this for every single character. It means that for every single character in this sentence, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 characters, I'm opening and close 11 times the file. And this is super expensive, okay? This is the right way of doing it. I have this as a string, I open the file once, I dump the string, and I close the file. And this is this is done once, not 11 times. Why? Again, the example is obvious. It feels artificial in the sense because I already have the string as a one single thing. It doesn't make any sense to do this. But as I told you, I have seen this done. For instance, think about processing DNA, processing different bases, processing data, whatever you want to process. And for every single iteration in the for loop, opening the file, dumping the data, closing the file, and doing that all over again. In the example, it's obvious you will never do that because it's even more coding. We don't want to do that. You will do only once. But in real time, in real life, when analyzing data, you may be tempted to do something like this. Bottom line is try not to do it. Recall, come back to the basics, to the basic examples, and recall, okay, this is bad because it increases substantially the amount of IOP. It may be necessary to save the data within the for loop, but if you are going to do that, open the file before the for loop and close the file after the for loop. So the file is not being open and closed all the time. Alternatively, probably the best approach is just store the data in a list type format and then save the data in this list format. We're going to see better ways to do that. But if you are in a situation like this, try to minimize, again, the message here is try to minimize as much as possible the number of file input-output operations that you do, because this is, in terms of performance, something that is going to really hurt you. Okay? Any questions about this example? All right. So just some things that I mentioned. It's important that you minimize the number of file input-output operations as much as possible. This input-output is another way to mention input-output operation. It's almost always the slowest part in any data pipeline. If you do a lot of file manipulations, try to minimize the IOPS. There are different tricks or techniques. Just let me know. I can make some suggestions. For instance, one of the things that you can do is load everything in memory. Of course, there are always constraints, right? If you have enough memory, if memory is an issue, then you may need to do some other alternative approaches. But if you can fit everything in memory, load everything in memory. Reuse data. Don't keep reading it from your files. If you must keep writing to temporary things to this doesn't work in all the operating systems. But again, if you are in a Mac OS or in Linux, use something called rundisk. Rundisk pretends to be a file system, to be a hard drive basically, but it's part of the memory, and memory is way faster than writing to the hard drive. So keep your results in memory and then write your results in one shot when you are finished. That's what the example showed. And the final comment, this is where we are going after this slide, is instead of using text format, which is slow, and we're going to see why, use binary files, binary file formats. Okay. So it's a small recap of what we have seen so far related to text formats. Now, let's start by asking the question, what is inside a file? So the first thing that you will notice, and probably have been using computers for a while now, is that there are different types of files in your computer. We have text files. Basically, these are files that you can double-click, open with Notepad, with your text editor, code editor, and you will basically see characters, and that is it. Although it's not as simple as it sounds, what is stored in the computer itself are not those characters, are what we call bits of information. And these are encodings for us to see as characters, but the computer don't see that. The computer doesn't see that. It sees just combination of symbols that encodes for us as characters that look like text. Ideally, this is not necessarily true, and sometimes when you do cross-operating system things, this start to be noticed. Ideally, there are unique assignments across languages, but not always true. So sometimes portability issues may arise. The other option is binary formats. And binary formats are not so appealing for humans because there is no this direct translation. If you try to open a binary file, the computer is not going to like it much because it doesn't know really how to display this information for you. It does know how to understand it because it's the language that the computer understands, but it's not too appealing for humans to be seen. So this corresponds to a variety of different things. Executable files are binary files. Meaning like if you open your browser, that's opening a binary file that the computer performs certain actions, but also can be used for storing data. And this is where we are going after here, because it's very efficient, because it's basically an image of exactly what the computer sees, and it doesn't require any post-processing or interpretation for display the data to us. It's very efficient for being saved in terms of performance, but also in terms of space. So there are good binary formats which allow us also to include what we call metadata, means information about the data itself. The examples I may show you today, depending on time, is one called HDF5, which stands for Hierarchical Data Format, or NetCDF. That's another one that is well known. So just a quick word about text formats. You may have heard about ASCII encoding. That is using certain number of bits to represent a character. And there is a table of conversions between what ASCII code is used and what character is represented. We're not going to dive too much into that. And there are some numbers there, how many possible characters you can use, and so on. Some characters are actually control characters that are used for instructing things like a new line or things like that. But important things to bear in mind is it basically needs about 18 bytes versus 8 bytes in binary to represent a character, which make it quite inefficient. the representation, as I mentioned, has to be computed. So that makes it a little bit slow. And this is a caveat when we are working with real numbers, with floating point numbers, with decimal numbers. The representation cannot be necessarily accurate. Meaning, if you have a number and it has 16 digits after the decimal point, when we are trying to convert that number that is a result of a calculation and store as a text in our files, we certainly will lose some precision. So it turns out that when this conversion happens, the computer is able to handle and do the computations in memory exactly for that particular number. But when it's being saved into the text file, there may be some corrections and some variations because of the representation. At the end of the day, it's not really crucial. It depends a lot on the field that you are working or using, but it's something to be aware of. Okay. So inefficient, slow, and in some cases, not an exact representation of the calculation carried out. Okay, so 3 things that are not necessarily a selling point in the text representation. Okay, now binary formats is a different way of storing information. The data are output to storage in the same format in which is stored in memory, so there is no translation needed. Why bother about this? Well, it's fast and space efficient. So let's take a quick example, a quick look at an example. This is saving 128 million doubles. So doubles are numbers, a way to call them numbers, floating point numbers or decimal point numbers. So we have 128 million numbers. If we are going to save it in ASCII, and this is a comparison between one of the file systems in our supercomputers and then the memory. If we're going to save in ASCII, you can see it's roughly the same amount of time it takes, 173 seconds and 174. So it doesn't really matter much because most of the time is being spent in the conversion. But if we're going to save in binary, it takes 6 seconds versus 1 second. So the important thing to bear in mind is when you use binary is, at least in this particular case, which is, think about almost 100 million numbers in a vector, that's the example I'm after, is at least 2 orders of magnitudes faster doing it in binary than in text space. Okay. One of the features, or not so much feature, but the disadvantage of the binary file format is that it's not human readable. But the question behind this is it really so bad? If you have 100 genes in a file, are you going to actually read them one by one? Really? I don't think so. You're probably going to use a tool like IGB or something like that to visualize the genes or any other type of data. You're not going to be looking at 100 million numbers one by one just to get a conclusion of that. You're going to probably plot those numbers or do something with them in a post-processing manner. So having access directly to that, yeah, it makes us feel a little bit more confident, but it doesn't really give you any particular feature, any particular advantage over the data processing itself. Okay. So I hope that with that, more or less, I have convinced you of using binary data. Now, there is one more element to consider, which is, okay, raw binary data. Basically, when we refer to raw binary data, is the data as the computer has in memory. It's the data as encoded by the computer. Basically, we don't format this data in any means. We just take whatever is in the brain of the computer and dump into a file. This is not such a good idea neither. And let me put you an example why. Let's say that we have a 2-dimensional array, a matrix, if you wish, with 100 by 100 numbers, decimal point numbers, floating point numbers. These more or less give you 40,000 bytes of information, okay? If you give someone these 40,000 bytes of information, no structure whatsoever, that person can, well, correctly infer that it's a 2-dimensional array with 100 by 100 elements, or it can also think that it's a 1-dimensional array of 10,000 elements, or you can think it's a string of 40,000 bytes, or something else maybe, because there is no structure around this data whatsoever. So obviously we need to tell this person, okay, whatever this data is, what I'm giving you, it has this structure or something like that. So it implies some additional form of communication, of information being shared with that person or the computer or another function or whoever. Well, this is usually known as metadata, okay? And the good news is that there are some file formats that already include this feature of adding metadata so people can reconstruct the data that we give them as binary data. So let's take a quick peek at what binary formats are offering R. So R data is an R-specific format. It cannot be read by any other languages. It only works for R, but if R is what you use, that's okay. RDS is another specific format of R, but it only stores one single R object. It can be only one variable, one list, but only one of them. These last two are the really good ones. These are kind of universal. They can be read by different languages. They can be read by different operating systems, are operating system agnostic, are platform agnostic, are really, really good, are what are considered the professional data sharing file formats. Okay, so having your files, your programs, writing in netcdf or HDFI file formats are considered like really professional programming programs, okay, or programming approaches to saving data. So netcdf is what we call a self-describing format. It means that when you save a file and you are saving this two-dimensional array, the file format knows and can communicate that to a different program reading that data. So there is no extra layer of communication that is needed. Just sending the file has that as part of the file. Contains not only the data, but also names and descriptions, a lot of goodies there. HDFI is another standard self-describing format, almost a file system itself. As we discussed at the beginning, you can have folders and categories and a bunch, even include images. Is really, really, really powerful. And many bioinformatics packages use this as a backend as well. So again, it's really good to be familiar with either netcdf or HDFI. Some other disciplines have their own binary formats. There are a great variety of them. So it's sometimes useful to know, depending what you are doing, the type of research that you're doing, that you get familiar with them, but try to always focus in the ones that are standardized in a way that includes metadata, and you are not necessarily dealing with the raw binary data, okay? So any questions about this? I don't think we will have enough time to cover all today, so we're going to probably split this set of slides for today and next lecture. But any questions so far? Okay, let's see how far we can go. I'm just skipping I think we can reach up to, well, we will see. We have 10 minutes, so I don't want to crush you guys with everything. So let's see some examples of the R data type, okay? I told you can say this using the save function. This is binary data, raw binary data, not structured, but that will recognize it still. So for instance, let's consider that we have two variables, variable 1 with the value of 10 and variable 2 with the value of hello, it's a string. And I'm using the semicolon here to separate two commands in the same line. So I can use save and then write as many variables I want and then specify what file, okay? So say var1, var2, and then file equal mydata.rdata. Now, I can exit R, open a new R terminal, and then load my data saying load my data.rdata. And now the variables var1 and var2 will be loaded in that way and accessible. So if I do print var1, it will show the value of 10. If I do print var2, it will say the string hello. Okay, these again are stored as binary data, so are very efficient in terms of storing things. And actually, if you try to open this file, you double click on the file, it won't be able to show to you because it's not text anymore. It won't show anything. It will say, I don't know how to read this file because it's binary data. But it's very efficient in terms of saving space and also in terms of speed when you save the data. Okay, so that's the first type, R data type. Any questions about this? Okay, By the way, this is the same thing. Some of you may wonder when you exit R will ask you, do you want me to save your session or your environment or something like that? Well, that's exactly what R does. If you say yes, it takes all the variables and use this save function to save all the variables in a particular file that is loaded every time that you restart R. Personally, don't like that. I hate that because, you know, sometimes I'm testing things and I don't want to have my environment all the time polluted with the same things, and I'm trying something. And if I do that, every time I open R, will bring that along. There are ways to remediate that if you have gone through the mistake of saying yes. But if instead you want to save your workspace because something that you have been developing, you want to keep the history of commands, the variables that you can create, you can do save.image. If you do save.image, it does exactly the same as telling R, okay, yes, save my session when I exit. Best way is to say save.image and then give a name to the image. Okay, and then you can load your image whenever you want, and you can have multiple images for different projects and things like that. So it's a more controlled way to actually store whatever you have been working with in a given moment of time. Okay, but this data again is saved as binary data by R. Okay, just thought about mentioning this because you know R has this compulsory behavior of asking, do you want to save the environment, do you want to save the things, and sometimes you just want to exit R and you may answer yes, and this is exactly what R is doing behind the scenes. Now let's take a look at the other file, the other binary file format that R offers. RDS is an R data single object. That's what RDS stands for. It only is restricted to one single object. Sometimes you just want to say a list, a file, something. Sorry, a list or a vector, something like that. Now, the important things in terms of performance, it doesn't really matter much here, but is that the object is serialized during the saving, which may, again, depending how much data you had to save, this can be not so good as the other case. In any matters, the main difference with the R data format is you can store only one variable at a time. So for instance, here in my example, A is a vector from 1 to 10, and I'm using the save RDS function. That's the one that generates an RDS format. I specify which variable, and then I specify what is the file name I want to give to that data. The advantage of this is that I can rename, I can load the data using read RDS and give the name I want to the variable that I'm loading. So that's one of the advantages that the single object stored binary data offers. You can load this in a particular variable instead of bringing back with the names that were given originally to the variables. Okay, and again, this is a binary format, meaning that if you try to open the mydata.rds file, you won't be able to see anything because it's stored as binary data. Okay, so two options so far: save, which generates an R data file, or save RDS, which generates an RDS file. All right. Any questions about this? Okay. Now, this is a comment related to the previous file formats I mentioned that sometimes are used in different fields in bioinformatics. If you are using a SAM format, it's better to use PAM. So this is the binary format of SAM, or even better, CRAM. This is provided by the RSAM tools package. If you are used to SAM tools to run from the command line, there is an R interface to that, which is called RSAM tools. If you are using FASTA files, it's better to use FASTQ or switch to BFQ. Again, these are binary formats from the FASTA template files. If your data is from P-Link, it's better to use BED, which is the binary version of the PAD files. And again, this can be achieved by the RTrack layer package. There is almost certainly a version of whatever file format you are using. And if not, you can always come back to these raw binary formats from R data and RDS. Not the most or the better solution because they lack of the metadata associated with the data, but still better solutions than just plain text. But let me clarify something because I get this question many times. it's not that it's not allowed to, or it's not good to use text files. We sometimes need to use text files for saving reports, for saving parameters or things like that. Even the code is text files. It's when you have humongous amount of data, copious amount of data, that the operating system will start to notice the difference in the speed and in the size. Okay, so it's not black or white. There are some different shades of gray there, but when you are dealing with humongous amount of data, definitely going to a binary file format is the option to go. And as I say, especially if you are using one of these standardized versions like NetCDF or HCFI, is the professional way to go. A few more different formats. ADGNet and Pegas can read FStar, Genetics, and Shinopop. Here, FStar, the track layer also reads weak and big weak. And there are many others in the current repository. So just to let you know, these are a few of the ones that have been collected during the years that some people had been used in different disciplines. Another good place to check for this is Bioconductor. So Bioconductor has a lot of packages related to bioinformatics processing and data formats. Okay. All right. Let me see how we're doing with the time. Almost there. Okay. Let me talk a little bit about metadata, and we're probably going to stop with that. Okay. So we kind of talk about metadata. It's simply put, it's just data about the data that you want to try. So the best binary formats has the metadata baked right into the file format. And these are the examples I mentioned, NetCDF and HDFI. In this way, the metadata and the data are never separated, and you don't need to worry about communicating either other users, the functions or programs, what structure the data have, what units the data have, when it was collected, using what particular version of a particular experiment. All that can be stored with the data itself in the same file. It's always good to include the metadata. For instance, nowadays, the very prestigious journals require that you also deposit your data for the papers that you are publishing, and that includes the metadata associated with that, meaning how you collected the data, which version of the particular software that you used to analyze were used, your pipeline, different things, all part of the metadata of analyzing and processing the data. So again, something to really keep in mind and start thinking about storing the data together with the metadata. What does include metadata? Well, of course, your name. In the same way I asked you guys to put your names in your scripts, or it's a good idea that you do, your names, the author of the data, the date and time that the data was created or manipulated or processed, the name of the code that you used, the version of the code was used to create or analyze the data, where it was created, what operating system. As I have mentioned, sometimes moving data from one operating system has some side effects, so it's always good to declare that. Values of key variables that were used to create the data. If you're running an experiment, if you're running a simulation, what about the parameters that you use? Those kind of things. Basically, you can include anything and everything that may help you in 6 months or long time from now to answer the question what, where, why, or how of the data, to reproduce this data or the analysis of the data. Anything that allow you to trust the data, basically. Again, nowadays we are in the era of reproducible results. It's a key element. So anything that allow you to get results reproducible, that's what we are after here. So kind of I mentioned many of the things. This is more aimed to if you're obtaining your data as simulations or compilation of programs, then parameters, when it was run, the version of the program, the version of R. If you are running this through R, what version of R, in which operating system? Again, these are crucial elements for being able to reproduce the results and the execution of these scripts. And I think I'm going to finish with this, and we can talk a little bit about the different formats because we won't have enough time for them. Some of the formats or the formats that we are going to look at are HDFI with hierarchical data format and NetCDF or network common data format. These are the most common ones and widely used across many different disciplines and fields. So they are something that people will immediately understand and have tools to read the data. You can read the data from R, or you can even read the data from APIs, from other tools that allow you to access the data. Which are the benefits of using this? Well, are provided by libraries. So again, not only in R, you can read this, you can read in Python, in C, in Fortran, you name it. All the programming languages has libraries that allow to recover the data from a HDF file or an SCDF file. They are self-describing, meaning that all this metadata we were talking about is also part of the file. They are included as elements in the file. Many of them are binary agnostic, meaning that they are portable between different operating systems. So if you're running a Mac or Linux or Windows or who knows what other computer, you can even read the data across this. Many of them supports parallel input-output operations, meaning that if you are running a program in parallel, there are tools to actually store this data into these file formats, improving the performance of the code. And they even had broader tool supports like visualization and analysis tools that can be done even with GUI if you need it. Okay, so as I say, I don't think we are going to have enough time to cover these 5 formats today, so I'm probably going to stop here. Ask you if you guys have any questions. As a reminder, because we didn't have the office hours on Friday due to the holiday, we're going to have office hours tomorrow at 1 p.m. and also on Friday, also at 1 p.m. And again, if you do have questions during the day or something you want to discuss, you're more than welcome to post on the forum or shoot me an email to courses@signet.utoronto.ca. But if you guys don't have any questions, maybe we are going to stop here. We're going to finish this batch of slides next Monday. And my plan for the rest of the lectures is to move into statistics a little bit. But I will be interested to know if you have any particular field or topic that you would like to cover. We have covered the basics of programming so far, in particular the features of R. I think we're going to do 1 or 2 lectures on visualization, maybe 1.5 lectures on statistics, general aspects, because R is big in statistics. But we may have room for 1 or 2 lectures to accommodate any particular topic of interest. It could be high performance R, meaning how to parallelize your R codes. It can be machine learning topics. It can be neural network topics. Or anything else that you guys may be interested. I hope that I could help with that. So if you guys have any particular interest, and you know, you want to let me know, we can try to accommodate that. Otherwise, of course, I will just follow the usual topics I cover. But again, there is some room there to accommodate 1 or 2 topics depending on what you are interested in, and if not, we will just follow the standard list of topics that is listed also in the itinerary for the course. Okay. Okay. All right. So from my side, this is what I have for you guys today. We will finish with this next class. And if you guys don't have any questions, we probably will stop now. All right. Okay, everyone. So I may see you tomorrow during office hours or on Friday, or if not, next Monday. Okay.